our final speaker for this session 2, Duncan Thomas from University of Southern California, individual variability and sensitivity to environmental exposures and implications for risk assessment. Duncan.
Thank you. So I've got a couple of things that I've thought I would address. I'm going to start by elaborating on some of the points that Joel made this morning about the effects that heterogeneity has on shapes and levels of dose-response relationships and how we should use that information in risk assessment. And then I'm going to focus on specific risk factors. And most of my remarks will be based on genetic risk factors, starting with measurable factors, either from candidate gene studies that we heard about from Nat this morning, or genome-wide association studies, what I'm now calling GWIS, gene environment-wide interaction studies. I can't claim credit for that term. It was invented by Mu and Curry. But then lead into unmeasured genetic risk factors. And there's the theme that I want to exploit about how we could use GWASs as a way of learning something or other about residual genetic heterogeneity. Then very briefly, following on Harvey's very nice talk just now, I want to elaborate a little bit more on approaches to getting genetics into PBPK models. He's done most of the work for me, so that can be pretty brief. And also elaborating on some remarks that from this morning about epigenetics. Again, I can be fairly brief about that. Just conclude with some thoughts about safety factors and whether there's any real reason why we should be trying to regulate residual heterogeneity. So let's start here. It's widely pointed out that there are smokers who live to a ripe old age without getting lung cancer. And there are other people who get lung cancer at a young age who've never smoked a cigarette in their lives. And there's no question about what that's a true description of what we observe. Many people go on to say that this proves there has to be some variability in susceptibility. Ain't so. This is a point that I heard one of the Pitos make several decades ago. I've been trying to track down this quote without success. If anybody knows where this quote comes from, I would love to see it. But basically, they argue that cancer is a stochastic process, and one's going to see variability in ages at death, even in the absence of any real heterogeneity between individuals. So this plot just simply demonstrates this. This is hypothetical data. Oops, I'm sorry, wrong button. This is why I hate these devices. I'm always pushing the wrong button. There we go. So which one here is the mouse? I mean the pointer. Let's try that. Yeah, okay. So the blue line here represents the cumulative incidence of lung cancer in non-smokers. And we see that some non-smokers will get lung cancer at relatively early ages. Let's say 0.5% of them will get lung cancer by about age 70. And there's the survival curve for smokers. And we'll see that some of them are going to, maybe 1.5% are going to live to a ripe old age of 100. And these curves were generated with no assumptions about any individual heterogeneity. Okay? So let's just talk philosophically for a moment about what we mean by uncertainty here. There are really two sources. One of them is our uncertainty about what the underlying, our imperfect knowledge of reality. If we could really observe what's going on in every single cell and every single DNA molecule over the course of a person's lifetime, then arguably maybe we could in fact actually predict what their entire lifetime, what their age at death or age at onset of lung cancer might be. But of course we're not that omniscient. And so a piece of what we attribute to variability is simply our imperfect knowledge of the entire complex biological system. But then there's also the possibility that there's, fundamental randomness in the process itself. absent our knowledge. Obviously, there are quantum mechanical effects, which are probably not all that important in biological systems. But this, I would argue, fundamental stochasticity in the way that cells divide and all sorts of other things that are happening, and the way they accumulate mutations. And that we're never going to get away with. So, Einstein famously said that God does not play dice when expressing some discomfort with quantum mechanical ideas. These things have sort of filtered into epidemiology. The long series of papers by Sandra Greenland and Jamie Robbins on probability of causation sort of reflects this ambiguity. Their very first paper advanced this deterministic kind of view of disease, whereby it was a counterfactual setup. You tried to anticipate what would have been the outcome of an individual had they been exposed, and the outcome of that same individual had they not been exposed. We get to observe only one of them because they either were or were not exposed in real life. So you can't, in fact, actually observe this whole two by two table, only the margins of the table for different individuals. One set of margins for the unexposed, another margin for the exposed individuals. But conceptually, we can say that we're interested in these two off-diagonal cells, those where the people had their disease caused by exposure in the sense that they wouldn't have gotten the disease had they not been exposed, and these people that were prevented, and so on. They then went on to develop a proper stochastic theory of causation that I'm, as a statistician, much more comfortable with. Anyway, let's leave that aside now, and let's talk about the things that we can measure. So I'll call these the known knowns. What we can do is identify various specific risk factors or specific modifying factors, candidate genes, various other environmental interactions, and so on. So here, for example, taking those same curves I showed before, we might distinguish the risk, the cumulative risk of cancer in carriers of a, anybody else see that button? Oh, there it is. In carriers of a genetic polymorphism and non-carriers of a genetic polymorphism. This is observable in an epidemiologic study. Nat showed us plenty of examples, many examples of that this morning. Well, it's a reasonable conclusion then, or inference, that if we can demonstrate some of these things, that almost certainly there must be other genetic polymorphisms that we just haven't discovered yet. So we'll call those the known unknowns. We know by looking at studies of heritability what the total genetic contribution to disease risk is. So we can add up the effects of all of the risk indices, like both Nat and Joel showed us this morning, and conclude that the variability that's accounted for by the already recognized genetic polymorphisms is only a small fraction of the total. But we know that there is that total exists. So then what about the unknown unknowns? All right. So let's do the following thought experiment, sort of in the spirit of Greenland and Robbins now. Suppose we all had some preordained death time. We just don't know when it is. But suppose we were God and we knew what they were, and we just simply computed the distribution of these preordained death times across the population. We'd see some sort of a distribution. And if we were to draw the incidence curve, the marginal survival curve for the entire population, we'd see a curve which looks very much like the curves I've already shown you. They wouldn't necessarily be quite the same shape, but here's a worked example. So what I've done is I've simulated what's called a frailty model. It just simply assumes that there is some baseline risk of disease, which in this case follows a Weibull distribution multiplied by a frailty term. So a frailty is this interpersonal variability. And the first curve I'm showing you here reflects zero variability across the population. So everybody's individual curve looks like this, and hence the population average curve looks like that too. And as we start increasing the degree of heterogeneity, we see those curves starting to separate. They get wider and wider. Eventually, that red line just goes off the edge of the page here. Now we're getting pretty close to the situation of omniscience, where everybody's got their own death time, and you're going to die either right here or you're going to die right out here or somewhere. But you see some population average distribution. As far as if we had no way of quantifying what those risks are, all we would see would be the population average. It would look just like if the curves I showed you previously, where there is no heterogeneity. So that causes me to wonder, does it really help in a regulatory setting to be trying to allow for this residual heterogeneity when we have no idea how large it would be? And Greenland and Robbins would argue that that degree of heterogeneity, that frailty variance, for all we know, is potentially infinite. So at this point, I think it's important to establish the terminology that I'm going to use throughout the rest of the talk. When I use the word susceptibility, I'm going to be referring to this idea of a risk factor, be it measured or unmeasured, which alters the baseline risk of disease in the unexposed. So these curves here represent a variation between individuals on the y-axis in their risk of disease at whatever level of exposure they find themselves. So these are absolute risks that I'm plotting here. And now imagine that we convert those to statements about relative risk. So I'm going to move all of these curves down to a relative risk of 1.0 at the unexposed. And we see an interesting reversal as soon as we do that. The people who are at the highest sensitivity are the ones with the lowest slopes, and vice versa. And that's simply a reflection of the fact that I've moved this curve down and this curve up, and I've had to stretch the slope. So that makes the point that estimates about sensitivity are very much scale dependent. Whenever we talk about interactions, we need to be very clear about what scale of measurement we're talking about, whether we're talking about absolute or relative risks, for example. So when I use the word, come on, push it harder. Oh, it helps not to put my finger over the thing at the end. Can you advance it? If there's somebody back, no, she's not there. Oh, there we go. Okay, we got it. So I'm going to use the word sensitivity now to refer to factors, again, measured or unmeasured, which affect the slope of the dose-response relationship. And in this case, because I'm going to be anchoring these, because I'm assuming that this factor has no effect on baseline risks, it doesn't matter whether I talk about absolute risks here or relative risks. I'm going to get essentially the same curve. Right? So that's just a bit of terminology that we would do well to bear in mind throughout this discussion. So now, pursuing the themes that Joel introduced us to this morning, I want to talk about two distinct effects that heterogeneity has. And the first is differential survival, a sort of survival of the fittest effect, basically saying that with increasing age, the population is increasingly selected in favor of the less susceptible or the less sensitive individuals. This is a factor which is primarily comes into play only for common diseases or for those risk factors that affect total mortality. The other is what happens in nonlinear dose-response relationships, which is the main point that Joel was making this morning, over which we had some discussion during in the discussion period and over lunch. And the point here is that the average dose response, the observable marginal dose response in the population, is not the same thing as the dose response for the averagely susceptible or sensitive individual. And this will be true whether you're talking about a common or a rare disease. So to illustrate these 2 points, let's talk first about differential survival. So suppose we have a model in which, let's say it's a linear risk model. The relative risk is proportional to is linearly dependent upon dose Z, with a person-specific susceptibility, the intercept term, and a person-specific sensitivity, the slope term. And we're going to allow either or both of those coefficients to vary across the population. So suppose first that we allow the intercepts. Sorry, which one am I doing right now? Yeah, we're allowing the. So irrespective, what this is going to induce in terms of the population risk will still be a linear function of dose, but with coefficients that are now the population average intercept and the population average slope amongst survivors to age t. All right, so what happens now? First, let's suppose that we have a constant baseline hazard, but we have slopes that depend upon dose. So we have variation in susceptibility. Well, this result, which was pointed out by Clayton and Kaldor way back in the 80s, shows that what you induce is a nonlinear dose-response relationship in which dose appears not just in the numerator here as a linear term, but it also appears in this animal down here, which is basically your survival of the fittest term. It's a function of your cumulative risk to age t and the extent of the population heterogeneity in this frailty term. So there's a picture. Basically, each of these lines here represents the dose-response relationship at birth, linear, and the dose-response relationship at increasing ages, and you see it tapering off more and more as a result of this denominator term. Okay, but as I say, that's really only important for common diseases or determinants of total mortality. So what about nonlinear models? Start with the same model that I had before, a linear dose response with person-specific sensitivities and specificities, and now allow those intercept terms, the susceptibilities, to vary between individuals, but let's for now keep the slopes fixed. Everybody's got the same sensitivity, but they've got different baseline susceptibility factors. And we get a family of curves. And the key point here is that obviously the curves are going to be separated vertically because of the differences in baseline risks, but the slope of the population average curve is decidedly lower than the slope of any individual's curve. Okay? What happens if we allow the sensitivities, but not the susceptibilities, to vary between individuals? Now we get a more complicated function, and it's now got this quadratic term down in the denominator here, and so you get a complete change in the shape of the dose-response relationship. Very briefly, one other example to follow up on Joel's discussion this morning about threshold models. Suppose we propose a linear threshold model with a threshold dose below which people are immune. There's no effective exposure below that threshold. And we allow those thresholds to vary between individuals. So the difference between what I'm about to show you and what Joel did this morning is I'm assuming that these thresholds are log normally distributed rather than normally distributed. I actually have a bit of a problem with thresholds that relate to negative doses. I don't understand what a negative dose is, and also it seems to me that these various factors are likely to be acting multiplicatively, and that leads naturally to a log normal distribution of thresholds. So suppose here are three possible degrees, locations of where that threshold could be. A population distribution with a low threshold, average threshold, a medium or a high average threshold. And when you now compute the population average risk, all right, it's not advancing again. There we go. We get a family of curves corresponding to the low threshold distribution, the medium, and the high threshold distribution. All of these curves have the property that they have zero slope and zero dose, but there is no dose that's absolutely safe. Any microscopically small dose is still going to lead to a microscopically small increase in risk. And first-order Taylor series expansion will establish that this dose response is linear at low doses, the point that Joel was trying to make this morning. And you could go through the same calculations if you assume that let's fix the population average threshold, but simply vary the degree of variability across the population. And again, you get similar curves. They differ more dramatically in shape, and they actually cross over in this case. But they still have this property, of course, that they have zero slope at zero dose, but there is no safe dose, no absolutely safe dose. All right, so we've heard a lot about wanting to regulate the most sensitive individual in the population. Well, what do we mean by that? Who is this mysterious most sensitive person in the population? And what if we can't, if he's not a member of any recognizable class that whose risk we can estimate epidemiologically? So what do we do? Well, in principle, if we believe the foregoing calculations, we could analyze the epidemiologic data under the assumed model and estimate that frailty variance. Of course, it would be a very poor estimate if we didn't have anything smaller than an infinite sample size. But even worse, we'd have to believe the assumptions that we're making of a proportional hazards model or a linear threshold model or whatever. And if those assumptions were false, which they almost certainly are going to be, we know, for example, that the proportional hazards model doesn't work for breast cancer and BRCA mutations. BRCA mutations have a bigger effect at younger ages than older. It is not a proportional hazards model. So we would get entirely the wrong answer if we did. So let's forget that idea. What we can do, of course, as we saw several times this morning, we can estimate the degree of variability due to known risk factors. Well, what about unknown modifiers? The contention I want to develop now is that we can use heritability estimates to get a handle on this. So before talking about exposure-response relationships, I want to talk just in general about how heritability estimates work so that we can set the stage for how you could estimate the heritability for gene-environment interactions. I think I've said all of this, and as have several people before me. And this is basically the kinds of models that Nat was showing us this morning about involving gene-environment interactions, and one slide simply to point out how complicated they could be. This is the oft-quoted paper by Loic Lemarchand on a very complicated apparent four-way interaction between two environmental exposures, smoking and well-done red meat, NAT2 and CYP1A2. Nat, I wrote that this was bladder cancer, but I suspect, do you remember this is bladder cancer or colon cancer? Doesn't matter, it's one of the two. And the key point I want to make is, of course, this is very unstable. It's all driven by this person, these individuals way over here who have the high-risk combination of genes and the high-risk combination of environmental factors. And there are, you can't read the sample sizes up there, but there are 12 individuals, 12 cases and 2 controls. So, look at the width of that confidence interval. That's really, if you try to do a bootstrap experiment resampling, that ain't reproducible. I was asked to say a few words about study design for GWIZ, and all I'm going to do here is put in a plug for a couple papers from our group on two-step estimators for looking at gene-environment interactions in GWAS data. This paper derives from a former PhD student of ours, Cassie McCrae, who basically advocated a two-step approach where the first step is essentially a case-only analysis of gene-environment association under the assumption that most GWAS SNPs are not going to be associated with exposure in the source population. And to achieve independence of the first and the second stage, we don't use cases only. We use the combined case control sample, and on that basis filter out a small subset of variants that we're going to carry forward to the next step. And then we test those with conventional case control approaches. Another variant of this approach is several papers that describe different forms of empirical Bayes compromises between the case only and the case control approach. which try to leverage the greater power of the case-only approach while achieving the robustness to misspecification of that gene-environment independence assumption that you get for the case control approach, appropriately weighting the two estimators so that if you have evidence against gene-environment independence, you're going to favor the case control, otherwise you favor this estimator. And a nice pair of papers in the January AJE issue of this year provides some empirical, I'm not going to walk you through this. This is just a screenshot that illustrates the comparison of power between the many different approaches that have now are now out there. These are all the different estimators that have been suggested. And the answer is, which is the best? Well, it depends. And you have to read the paper to find out it depends on what. Another brief point, simply to make that you need huge sample sizes to have any reliable power for detecting gene-environment interactions. This is what you might get for a typical gene-environment study involving a candidate gene. And for a GWAS scan, where you're going to be testing at significance levels of the order of 10 to the minus eighth rather than 0.05, you could easily require sample sizes in the tens to hundreds of thousands of individuals. So what about this idea of unmeasured genetic variability? Let me briefly introduce you to the idea of polygenic models. And I'm going to skip over a couple of things to get to the meat of this. The basic polygenic model entails the assumption that a trait is determined by a sum of a large number of genes, each with small effects. And then by application of the central limit theorem, you can show that the correlation within a family of the trait is going to be, well, the trait will be multivariate normally distributed with an independence piece representing essentially the residual or environmental risk, and the piece which depends upon the kinship matrix, the degree of relationship between individuals within the family. And what is called heritability, or more precisely, narrow sense heritability, is the proportion of variance that's attributable to the additive effects of genes. So it's the portion of the total phenotypic variance that's attributable to this K term. Okay? And stuck again. Next. If you have a binary, that's all well and good if you've got a continuous trait like height. If you have a binary trait like disease, then you basically propose that there's this underlying continuous normal distribution of a susceptibility factor here. It's called liability. And if you're above the threshold, you're affected. So given estimates from family data of sigma squared and tau squared, you can now then proceed to estimate what's the population distribution of total genetic variability. I'm going to skip over the next little bit in the interest of time. These are a couple of slides from several key papers that have talked about how you can estimate the percent of variance that's explained by known and unknown genetic risk factors. I'll just leave this up here for just a moment. This is from Peter Vischer's group that develops a theme that one of you this morning, I forgot now who it was, I think it might have been Fred, pointed out that we can use GWAS data to estimate that kinship matrix between all of us, one big happy family, because we are in fact all related, even though we may not know who's closely related to whom in this room. We can still estimate that from the ensemble of all of our GWAS SNPs. And that's the idea that I want to develop now in terms of exposure. Now, what we could do in principle is we could do a family-based study if we had the exposures on everybody and fit essentially a family history or a heritability by environment interaction term and do that. But the approach I'm going to describe instead that Dan Stram is proposing and we'll be discussing in more detail at the ASA Radiation and Health meeting this summer, uses the Fisher idea. But in the context not of looking at genetic variability as a main effect, but in terms of genetic variability of sensitivity to the environment. And so the second of the two approaches that he's suggesting is apply Fisher's method to case-only data. Estimate the kinship matrix for all pairs of cases, and then essentially regress those on the pairwise similarities of their exposures. So I contend that it can be done, at least in terms of the genetic determinants of the genetic component of inter-individual variability. In terms of other components, I haven't a clue how to do it. I don't think it's possible. So again, I'm going to skip over this just to make the two concluding points, one of which had to do with putting genetics into PBPK models. So this is following up on Harvey's talk. So he talked a bit about Bayesian pharmacokinetic models. Here's our own formulation of it. Imagine that we've got an exposure of interest. For epidemiologic populations, this would be extended over time, and it's leading to some perhaps complex network of intermediate metabolites, all given by a system of deterministic differential equation models with rate parameters corresponding to, let's say, activation and detoxification rates. Those, in turn, could depend upon genotypes at the respective loci, and then finally related to a disease outcome. And all this can be fitted with Bayesian Markov chain Monte Carlo methods. And then I think I'll skip the epigenetics because I'm supposed to have shut up by now, and just conclude by saying that I have great difficulty with this idea of trying to regulate using arbitrary tenfold safety factors to try to pretend that we are protecting the most sensitive individuals in the population. I have no problem trying to regulate demonstrable risk factors. So asthmatics, the young, the elderly, the diabetics, whatever, that's fine. If you've got the epidemiologic data to do that, carriers of various known polymorphisms, all that's fine. I have a great difficulty trying to regulate residual genetic heterogeneity, although we may be able to get a handle on that by using GWAS-based heritability estimates. And with that, I'll stop.
Why?
Why do I object to regulating residual heritability? Because I have no idea how big it could be, and it could be potentially infinite under my hypothetical scenario of predestination. Yes. I don't personally believe that, but that's the argument that Greenland and Robbins advance.
Sort of related to that, I worked with Kenny Crump for 12 years, so I'm a little sensitive to the distinction between linear and low-dose linear. And when you showed the family of curves for thresholds, that's so critically dependent on the width of the variability distribution, where the data is, and where the regulatory limit might be. I just wanted to make sure people, I assume from your answer that at the end there that you would agree that we really don't know what's going on down there. The fact that it may still add to dose at the lowest concentrations doesn't mean it adds appreciably compared to what you would infer by a extrapolation from the data much higher up.
Of course.
Risha Putzrath, again, the slides went rather quickly, so I'm not sure. I thought I saw on your distribution, your log normal distribution of thresholds, that the curve went through the origin. Is that correct?
I'm not assuming that there's any mass at zero, if that's what you're asking.
I'm asking whether, yes, that's what I'm asking. Is there...
I'm assuming that there are no individuals who are infinitely susceptible. That the distribution of individual thresholds is strictly positive.
Okay, and non-zero.
And non-zero, yes.
And yet, when you integrate to get the combined risk, it doesn't have that same margin away from zero?
In the limit, as dose goes to zero, the slope of the dose-response relationship goes to zero.
But you just said it doesn't reach the limit for one of the parameters. That's what's confusing me.
This may be something that's easier explained one-on-one, but
Okay. Thanks.
Thank you. Tony Fletcher from the London School of Hygiene. I was wanting to follow up on one of the points about differential survival. It sort of has some common sense that the susceptible should die out. And I was recently looking at this by coincidence, trying to get a handle on how big that might be, and looking at a large, I think it was the ACS, a large cohort of smokers. Mm-hmm. And in fact, the relative risk for lung cancer doesn't fall as you go into older age groups until very old age, I think 75 plus. It does go down with more common disease like heart disease. So I had the impression that although it was true that common diseases, you might find this, in fact, even a relatively common disease like lung cancer, it wasn't yet evident in the face of that strong exposure of culling out, in principle, the more susceptible. So I wonder whether that process of a residual, less susceptible pool is actually in danger of being, in principle it might be there, but in danger of being somewhat exaggerated. What do you think?
Well, that's a good point. But bear in mind that the figures I showed were based on assumption of a constant relative risk with age. And of course, for smoking, you've got a very complex exposure time response relationship involving, age at start and duration of exposure and time since quitting and so forth. And I would want to be sure that we properly take into account the right shape of the dose response, exposure time response relationship to begin with, before adding in the individual variability. Now, what you say may be quite correct. It could be that there are non-linear dependencies on age itself for lung cancer that could counteract whatever the survival of the fittest effect is.
Okay.
Again, that's something I'd be happy to explore with you further.
Yeah, this question does not pertain to non-cancer endpoints. But I'm listening this whole day and I'm saying to myself, wait a second, I was taught that there's an initiation process with whatever the complexities. And then there's the issue of the promotion of the tumor to recognizable cancer. And we've now said nothing about promotion. So here we are arguing about the number of angels on the head of a pin, when in fact there's another hammer out there which has to do with the promotion of the initiating event. Would you like to comment?
Sure, I very much would like to. All of what I've said, although it's based on very simple linear dose-response relationships, which for cancer could be you could imagine that that's the way one might model the probability of initiation. There's nothing in principle that wouldn't allow you to extend this to more complex models of carcinogenesis, like the Mogov-Carnudsen one, which formally incorporates terms for promotion, and the birth minus death rate, that's an inherent piece of for intermediate clones, could very well and also involve inter-individual variability terms.